So I'd like to briefly talk about this example here, this practice problem, which really sort of tests our understanding of molarity and dilution. So the question essentially says a 5.50 molar solution of lithium hydroxide was diluted from 45.0 milliliters to 125 milliliters. So sort of just digesting that first part of the problem, clearly we essentially have one beaker, so to speak, although this isn't really the form that beakers take, but we have one container within which we have a solution, and we're told that the molarity of the solution is 5.50. Um, it's a 5.50 molar solution. In other words, um, if you really want to go into the semantics of what what this M means, what does it mean to say 5.50 molar solution? Well, that essentially means that for every 1 liter of the solution, we have 5.50 moles of whatever compound it is we're talking about. In this case, it's lithium hydroxide, which is LiOH. So this is essentially what we have. And we can also infer that it's 45.0 milliliters to begin with. So really it's 45 milliliters, 0.0 ml. So really, I mean, the quantity, the volume of this solution is 45.0 ml. And that's essentially the first situation, right? That's the first scenario. And then, of course, we're given another scenario, which is to say that this particular solution with this molarity has been diluted. And when something's diluted, we're essentially just adding liquid to it and decreasing concentration, right? So in the second scenario, I mean, we have the solution, but it seems as though we have more water, right? More liquid. And so opposed to being just 45.0 milliliters, it is now 125 milliliters. So you've essentially increased the amount in terms of volume of the solution as a whole. Um, and what that would do to the solution is, well, it would just decrease the concentration of LiOH, of lithium hydroxide. And the idea is that it's more concentrated if it's in a smaller amount. But then, of course, if you increase the amount of liquid, then it's less concentrated. Um, but then the ultimate question really asks us how many grams of LiOH. Well, the ultimate question then says that from this solution, from this diluted solution, right? Not this one, but this diluted solution, we're essentially taking a sample. We're taking a sample, so you have basically a small sample of this solution, right? Of the same solution, but the one that is diluted, and this sample in terms of its size is 5.0 milliliters, right? And the idea is that it's asking you, it's essentially, given this information, it is asking you how many grams of LiOH are in this solution, right? In this solution, which solution are we referring to? We're referring to the one that is 5.0 milliliters. So the question isn't really asking you how many. The question is really asking you how many grams of LiOH of lithium hydroxide are in 45 milliliters. It's not even asking you how many grams of LiOH are in 125 milliliters. It's really asking you how many grams of LiOH are there in 5.0 milliliters. So it's really this three-step process. But what I really want to sort of make concrete is that this had its own molarity, right? The 45 milliliter solution had its own it had its own molarity at 5.50. In other words, for every liter, you essentially had 5.50 moles of the solution. But of course, when you add more liquid to the overall volume, then that ratio between solute and the volume as a whole, that ratio is uh, you know it's now expressed in a different proportion where you have less solute and more solvent in a way. So you would expect that you would expect that you have a different molarity in this case because the concentration level has decreased. And that is significant to understand. But really, if you wanted to just go into this question here, ultimately what you're really trying to ask yourself is, there really isn't any particular conversion factor that can take you from the information that we're given to grams of a compound. But if you're studying introductory chemistry, then you're probably well acquainted with the idea of molar mass. In other words, if you take a compound like LiOH, and if you add the atomic masses of the individual elements, then that is the molar mass. So LiOH, if you take lithium, lithium has an atomic mass of 6.94, and then oxygen has an atomic mass of 1.008, and then you add that to hydrogen, which has its own atomic mass of oxygen has 16 and then hydrogen has 1.008. So you do 6.94 and then add that to 16 to oxygen, and then of course you add that to hydrogen, or the atomic mass of hydrogen, and you would essentially get grams per mole. If you would do this entire computation, you would get 23.95 grams per mole. And so this unit is expressed in terms of grams per mole. And all that's trying to say is that for every 1 mole of this compound of LiOH, since you're talking about a molecule, you have 6.02 times 10 to the power 23, or actually for every 23 grams, forgive me for making this mistake, but for every 23.95 grams of this compound, you have 1 mole of LiOH. And so this is often used as a conversion factor. So if I asked you, well, if I gave you like, okay, 6 moles is how many grams of LiOH? Well, you would want to use this conversion factor, and what you could do then is just put down what you're being asked, which is 6 moles, and then using this conversion factor, place it in such a way that your moles cancel out. And then of course in your numerator, you would want to put your quantity of grams, and you would get your gram equivalent. And so that's essentially the idea that you want to abide by here. If it's asking you for grams, it would then be a better idea to find out how many moles are in 5.0 milliliters of this solution, which has a different concentration than the original solution. And once you have how many moles of lithium hydroxide are in 5 milliliters of this solution, then ultimately what you could do is use this conversion factor to your convenience, as we've done down here, and get a gram equivalent. And that's just basic dimensional analysis, or they call it the factor label method. So that's really not too complicated. But so, sort of trying to apply the same idea here, you could think that, well, okay, let me first figure out how many moles are in the original solution, and then use that as a conversion factor to find out how many moles are in the 5.0 in 5.0 milliliters, right? So that's your ultimate goal. But recognize that if you find out how many, if you find out how many moles, if you figure out how many, the moles will essentially be the same in both cases. So the idea is that, you know, whether you have 45 milliliters or 125 milliliters, you've just added liquid. So moles are going to be constant, right? You're not changing the amount of solute that you're adding. You're essentially changing the amount of liquid that you're adding. So in that case, your moles would essentially be the same. But if you were to talk about this guy here, 5.0 milliliters, of course, the quantity that you want to extract, the amount of moles would actually decrease, right? So that's something also to keep in mind. So the approach is to figure out how many moles are in 125 milliliters, and then apply that conversion factor to how many moles there would be in 5 milliliters. So what you could do is first use this information, right? Sort of use this information to find out how many moles there are in the first situation, right? So the information that we have at our disposal is that the original, and this is, I'll write this here, the original solution has a molarity of 5.50 and also has a volume of 45.0 milliliters. So this is enough. This is enough information to be able to attain how many moles there are in the actual solution. But just keep in mind that the molarity of this guy will be different. So right now we're here and we're just taking this step by step, but just keep in mind as we move forward, we may have to change some information to take into account that the molarity is different. So what you could do in this case is just say that, okay, you have 45.0 ml, and of course you want to express this in terms of liters, although because your conversion factor of molarity is itself moles per liter. So you would want to put your liter in the denominator and your moles in the numerator so that your liters would cancel out and you would be left with moles of your substance, which is actually what we want. But we can't do that if we have milliliters. So instead what we'll do is we'll change our milliliters to liters and we'll work our way forward from there as I've already described. So if you want to do that, you just put 1,000 in the denominator here because 1,000 milliliters is 1 liter. And then your milliliters would cancel out, and then you're just left with liters. So now that you have how many liters, I mean, if you were to stop here, you would just be left with how many liters are in 45.0 milliliters, and that's actually not what we want to do. We eventually want to work our way towards talking about moles of lithium hydroxide. And this is where, this is where the molarity comes in handy. This is why this is considered as a conversion factor. I've said that, any quantity with an M is just, a solution is present, and that quantity expresses how many moles there are per 1 liter. So really the conversion factor is exclusively in terms of 1 liter. So in this here, you could say that 1 liter, you're using this conversion factor that 5.50 moles is equal to 1 liter, or 1 liter has 5.50 moles. So 1 liter is 5.50 moles of LiOH, and that's essentially the compound that we're talking about. And so if you were to plug this into a calculator, you would essentially get how many moles are in 45.0 milliliters. And I'm just going to go ahead and plug this into a calculator here. And so you do 45.0, and then of course you multiply that by 5.50. And on the other end, if you were to do this, you would get 2.47. So you would really get 2.47. And since there are three significant figures, I guess you could say raises to 0.24, right, moles of LiOH. So, I mean, this works, right? We were able to, you know, if you want to find out how many moles there are, you need basically those basic constituents that can get you there. You would need milliliters, right? Because you want to know how many moles are in a particular quantity of volume, and you have that. We have that here, 45 milliliters. And of course, you need molarity, because that itself can actually allow you to cancel out liters, or of course even milliliters if you convert it to liters. And that canceling out will leave you with how many moles. And so, you know, to really adjust oneself to figuring out these connections and sort of unpacking conversion factors in particular quantities is a really important skill. And that only increases with the efficiency at which you do that only increases with familiarity, familiarizing yourself with the relationships between some of these conversion factors and proportions. Really, that's what they are, proportions. But you know, it's interesting because why couldn't we? And this is a common question in questions like this, sort of as a digression before we actually get to solving the problem. Why couldn't we just say 125 moles, or sorry, 125 milliliters, and then get how many moles are in this guy? Why couldn't we do that, right? And the reason is, so, you know, if you were to do that, right, if you weren't so aware, if you were to do that, you would do, okay, I have 125 milliliters, and I'm going to use this conversion factor, or actually, first let me express this as liters, right, as we did here. And then, of course, what you'll do then, if you're pursuing this route, what you'll do then is you'll say, okay, I want to cancel out my liters, and I want to be left with moles. And then, of course, if you were to plug this into a calculator, you would get a different amount. And that doesn't make too much sense. I think you would get 0.687 moles. And again, that is not consistent, right? It's not consistent because, you know, I had a particular quantity of moles in this solution here. And I had, and that same amount of moles is in this solution, except I've changed the amount of water, of liquid that I've added. So the mole amount shouldn't have changed. It doesn't make sense that it changed to 0.6887. It should have remained 0.24 moles. And the idea behind that, why it's different, not because it actually is different, but because 125 milliliters has its own separate molarity, right? In the question, it's given us both the molarity and the milliliters of the first situation of this one scenario. But now when it starts talking about another scenario, it's changed the amount of milliliters, but it hasn't changed, it hasn't gave us how much molarity that solution 125 milliliters consists of. So the molarity changes. So we were only able to calculate the moles in the first situation simply because we were given enough information, right? The conversion factor of 5.50 molar solution that allowed us to get to moles is only for 45.0 milliliters, right? It only pertains to that amount of volume. But when we change the volume, the molarity changes. So we can't actually use the molarity which pertains to a different volume, right? The proportion then is not, it's not balanced out. It doesn't work that way. So this approach would have been wrong, right? And then now that you have the amount of moles, so this is, let me just go ahead and sort of mark this as wrong. This would be a wrong approach. But sort of continuing with the correct approach, we now know that 45.0 milliliters has 0.24 moles of LiOH. That's sort of a relationship that we've established by what we've explained down here. And then you could think that, okay, I want to know how many moles are in 5.0 milliliters, right? I mean, that was the goal. And then you might use this conversion factor, and apply it here. You may say, okay, well, 5.0 milliliters is 45.0 milliliters, so that your milliliters cancel out, and you're left with 0.24 moles of LiOH. And then at the other end, you'll be left with an answer that is moles of LiOH in 5.0 milliliters. But that just isn't true. It's not consistent. Think about what you've done here if you took this approach. Think about what you've done. What you've done is this would not be the amount of moles that are in 5.0 milliliters, because the 5.0 milliliters was extracted from this solution, not this solution. So 5.0 milliliters here will have a different amount of lithium hydroxide in terms of moles per liter, right? And if you were to take 5.0 milliliters from this solution, you would have a different amount of moles per liter of lithium hydroxide. And why that is the case is because this guy is more concentrated and this guy is less concentrated. The more liquid you've added, the less amount of lithium hydroxide molecules per liter, or moles per liter. And here, since you have a lesser amount of liquid, that would essentially translate into being more lithium hydroxide moles per liter, right? So this would be an unhealthy conversion factor here, because it doesn't really express the accurate amount of moles. What you really want to do is take 5.0 milliliters, and you're just as you did before. But what your conversion factor would be that 125 milliliters of solution has 0.24 moles of LiOH. And that's consistent, right? I mean, we know that if we hop from here to here, all we've done is change the amount of liquid. The amount of moles of LiOH stay the same. And so it's not a problem for us to make this ratio, to make this conversion factor. We know that 125 milliliters has these many moles. And since we're taking the 5.0 sample from a sample which is from a beaker which is more diluted, it would make sense to use 125 milliliters as our conversion factor, right? That is what pertains to our problem. And that's essentially where we're grabbing the 5.0 milliliters from. So when we express our final answer in terms of moles, it will take into account the sample that was taken from the beaker, which was less concentrated. So ultimately, what you would do is you would put your milliliters down here, since they would cancel out, and of course you'd be left with 0.24 moles. And after you essentially plug this into a calculator, you would essentially have 0.24 and then divided by 125.0. Let's see here. you'd have 9.6. So if you would have 9.6 to the power 10 to the negative 3 moles, and of course you could unpack that by using the I forgot what they call it, but I think it's the scientific notation methods. But that's how many moles you have in 5.0 milliliters. But of course, briefly recall that our goal really wasn't to find out how many moles there were. That was sort of an intermediate approach. What we really wanted to do was figure out how many grams are in the amount of moles that are in 5.0 milliliters of this solution. Not this solution, but this solution. So you would just essentially, you know that 1 mole equals 23.95 grams. So you would use that as a conversion factor and say, okay, 9.6 times 10 to the power negative 3 moles of LiOH, of lithium hydroxide. And if you place your conversion factor in a correct manner, you would essentially just be doing, your moles would cancel out and you'd be left with grams. So you'd essentially just be doing 9.6 times 10 to the power, let's see, to the power negative 3. And you'd multiply that with 23.95. And you'd get 0.22, so you'd get 0.229, and then of course, you know, you could round that off to 0.2 to 0.23, right? 0.23, or if you're looking for accurate significant figure, depends on really what you want to do with your significant figures, but it would be wise to express this as the amount which carries the least amount of significant figures. So in this case, you only have 2, so you would round that to 2 significant figures, and that essentially would be your answer. So it's really important to essentially remember that that you know, certain quantities have molarities, but they're essentially confined to particular scenarios, right? We can't change the amount of if we have a container that has a solution in it, and that solution has a particular molarity of anything, and it could be concentrated with anything. We can't just go off and essentially just change. We can't go off and essentially apply. We can't go off and change the amount and then apply the molarity as a conversion factor of the previous volume. We have to find the new molarity oftentimes and then use that as a conversion factor. So that overlap, it's tempting, but it's not accurate.